Hello there, this is Socrates. Welcome to today's video on infinite series where we're going to talk about the ratio test. We're covering section 2K of our textbook. And if you don't have a copy, go to the description in YouTube for this video and you can find a link to Dropbox where you can download a copy, a PDF copy of our textbook. So before we talk about the ratio test, I would like to review a couple of definitions that we saw in our last video where we talked about absolute versus conditional convergence. If you haven't seen that video yet, it would be a good idea to probably see it first. So, a series is absolutely convergent if the series where we take the absolute value of all the terms converges. So we can start out with an alternating series, let's say, or a series more generally where some terms are positive, some are negative. Turn all of the terms positive by taking their absolute values. Check out that series, see if it converges. If yes, then the series is absolutely convergent. However, if that series with the absolute values diverges, and in this case it has to diverge to infinity because all terms are positive, but the original series still converges. Okay, so maybe you have an alternating series, you can apply the alternating series test, and then you discover, oh, okay, the series that was originally given to you converges. Then the series is called conditionally convergent only. And we saw in the last video that there is a stark difference between these two kinds of series, because if you rearrange the terms of an absolutely convergent series, you always get a convergent series, and it must converge to the same exact sum as the original absolutely convergent series. You have almost the complete opposite for a conditionally convergent series, because you can pick your favorite number, let's say pi, it was just Pi Day very recently. You can make a conditionally convergent series add up to pi or any other number that you wish by finding a suitable rearrangement of the terms. So it's very bizarre. You don't want an infinite series that will give you a different sum just by moving some terms around. So we have said that an absolutely convergent series is definitely superior to a conditionally convergent series. You can almost tell from the name, absolute versus conditional. You don't want conditions on your conversions, right? And another great thing is that if you can test your series for absolute convergence and it passes, you find out that it's absolutely convergent, then you don't have to bother testing the original series. It will also converge. All right, so with that, let us go and see what the ratio test says. All right, here we are, section 2K, the ratio test. Suppose we're given a non-zero sequence, a sub n, and the limit of the ratio an plus 1 over an exists. Say that is equal to L, in which case it is either 0 or a positive number. In other words, it cannot be negative, or maybe it's positive infinity. If the limit is smaller than 1, possibly 0, then the original series that we get from summation of a sub n is absolutely convergent. However, if the limit is bigger than 1, then the original series a sub n is divergent. If the limit happens to be exactly 1, which does happen, then the test is inconclusive. We cannot use the ratio test to form a conclusion about this infinite series. Okay? So this hopefully reminds you of something that we have seen recently, which involves a ratio, except it's different. You remember we saw something about a sub n over b sub n, and that was the limit comparison test. So the ratio test looks a little bit similar, except we take absolute values, whereas in the limit comparison test, we don't take absolute value because all of the terms are already positive. So it's pointless to take an absolute value. So here it is important that we take the absolute value of the ratio an plus 1 over n, and then we'll see if we can find a limit for that ratio. If it so happens that the limit does not exist, once again, our test is inconclusive, so you cannot say anything. Notice also that we can only conclude that a series is either absolutely convergent or divergent if part A or part B applies. There is no part that says your series is only conditionally convergent. So in other words, your series is either very good or it is bad. There's nothing in between. All right, we will prove this test later, but for now, let's take a look at a basic example. All right, here is an infinite series, which is alternating because you have negative 3 to the power n. And we're going to divide by n factorial. Okay, so that is the factorial symbol. And just to remind you, this is something that we often see in pre-calculus or certainly basic calculus, because when you take the derivative of a monomial, the power comes down and the power decreases. So eventually, if you take enough derivatives, the factorial of the power comes out. Okay? Reminder that by definition, 0 factorial is not 0. It is in fact 1. Okay? But n factorial is defined as a product. So you start with the highest number n, and then you multiply by the number right before that, n minus 1, and then the number right before that, n minus 2, and you keep on going, etc., until you get to 2 and 1. Okay? So another way to see this is to think in terms of increasing order. If n is bigger than 1, let's say, although 1 factorial by definition is simply 1, then you just write out all the integers between 1 and n, and you multiply them together. Okay? So for instance, 5 factorial is 5 times 4 times 3 times 2 times 1. Okay? It's obviously it's irrelevant to put the 1 there, okay, but just for the sake of completing the definition, we'll put it there. So 5 times 4 is 20, times 3 is 60, times 2 is 120. Okay, so obviously the factorial function grows very, very quickly. You really don't want to see what 10 factorial looks like. Maybe you'll still be able to do it on your calculator. Let's ask Maple, are you able to do this? And yeah, no problem. Okay, 20 factorial, yeah, you might have a problem with your calculator on that one. Okay, the factorial, you might say, okay, what about 1/2 factorial or 7/5 factorial? Yeah, we don't really have a definition for that when we have a fraction or even a negative number. Okay, what is negative 3 factorial? Yeah. But there is something called the gamma function, which is part of advanced mathematics that enables us to basically extend the definition of the factorial function. But we are not here to do that. We are here to think about the ratio test. Right? So we have a sub n is this term, negative 3 to the power n over n factorial. Right? So what we want to do is take the ratio of an plus 1 to an. As a warm-up, let us see how to properly compute an plus 1. Okay? So what I always tell my students is, if you're doing this on your notebook, encircle the letter n wherever it appears. Okay, so it appears twice. And where it appears, if need be, wrap it around parentheses and then add 1. Okay, so if we do that here, you'll have n plus 1 in the exponent. Is it really necessary to put the parentheses there? Maybe not. Okay, however, in the denominator, you had better wrap that n in parentheses because n plus 1 factorial is going to look ridiculous. Like the n is no longer factorialized, okay? So you need to put parentheses around the n plus 1, in this case, in the denominator, okay? So we are going to take the ratio where this is in the numerator and this is in the denominator, and then we're going to take absolute values. But before we do that, let us simplify this a little further, okay? Because once we take the ratio, we're going to want to simplify it because we're going to take a limit. So if it looks complicated, we might not be able to see what that limit is supposed to be. Okay, we have an exponent here, n plus 1, and we know from the rules of exponents that we can separate this into two factors, minus 3 to the n multiplied by another minus 3. Okay? Now, what about the n plus 1 factorial? All right? So here is 5 factorial. If we want 6 factorial, what do we have to do? Okay, so check it out. Let's make a copy. If you want 6 factorial, then we will want 6 times 5 times 4 times 3 times 2 times 1. So we can see that 5 factorial, of course, is part of 6 factorial. We get 6 times 5 factorial, and we know that 5 factorial is already 120. We already computed that, so all we need to do is compute 6 times 120, which gives us 720. Okay? The important thing here is to recognize the pattern. If you have 6 factorial, you can write it as 6 times 5 factorial. So in general, if you want n plus 1 factorial, then you can write this as, let's make a copy, you will have n plus 1 multiplied by n factorial. Okay, so let's put the n over here, and you have n factorial there. All right, let's exaggerate by putting the times symbol. Which one? How about this one? Okay, so we have n plus 1 times n factorial. 6 factorial is 6 times 5 factorial. All right, n plus 1 factorial, one more time, is n plus 1 times n factorial. Okay, so now we're ready to compute the ratio and find its absolute value. All right, so we need the limit as n approaches infinity, and the ratio test says put an plus 1 in the numerator and an in the denominator. So here is an plus 1. It goes in the numerator, and an, the original term, goes in the denominator. Okay, now many times fractions appear when we are using the ratio test. So with practice, you could probably skip to what we're about to do, the second step, where we are going to multiply the numerator with the reciprocal of the denominator. Okay, so it becomes numerator times the reciprocal. So we will put n factorial in the numerator and negative 3 to the n by itself. I can delete this symbol now. We will put minus 3 to the n in the denominator. Okay, so yeah, instead of wasting your time on this step, just flip this fraction over, because you know algebra, and do a product instead. All right, so now we get to simplify this. We're going to take, because we need to take a limit. Notice how rewriting n plus 1 factorial into n plus 1 times n factorial will allow us to cancel these two factorials. N factorial, those go away. You have a 1 in that numerator there. Oh, and there's more. We have negative 3 to the n and negative 3 to the n, which also cancel, and that leaves a 1 down there, and this goes away. So there's still a negative 3 in the numerator, but we're taking an absolute value. So we are simply going to get, that goes away, positive 3 over n plus 1. Oh, n plus 1 is positive. So we can actually remove the absolute value symbols. And as n goes to infinity, n is getting bigger and bigger and bigger, that limit is going to be 0. Aha! And let's see. Let's go back and see what the ratio test says about this limit of 0. All right, the limit that we got is 0. We are in part A. 0 is smaller than 1. So our original series is absolutely convergent. Yay, let's write down our conclusion. All right, since L equals 0, which is smaller than 1, by part A of the ratio test, we don't really have an abbreviation for the ratio test. The ratio test, we can conclude that our series is absolutely convergent. Let's put it on the next line. All right, so if it is absolutely convergent, then of course the series without absolute values also converges. Our original series also converges. There's actually a nice bonus result here, and it comes from the divergence theorem or the divergence test. More accurately, it comes from the contrapositive of the divergence test. If you remember from that video, we said that if a series, if the terms of a series do not go to 0, then the series must diverge. And we did it by proving the contrapositive, which was if the series converges, then the terms of that series must have limit 0 as n goes to infinity. So by that contrapositive, since that series converges, then we can also conclude that the terms of the series get smaller and smaller. They get closer and closer to 0. So let's write down that bonus result, bonus conclusion. By the contrapositive of the divergence test, we can conclude that since our series is convergent, our original series is convergent, the terms of that series must approach 0. So, in other words, the limit as n approaches infinity, I can steal this symbol, of our terms, which was this one, it's here. All right, this is our a sub n, must be equal to 0. Okay, that's not very obvious because you're taking a power of negative 3, and we know that exponential functions are also powerful. Okay, 3 squared, 3 cubed, 3 to the 4th, those numbers get big very quickly. Oh, and we also said if it were all by itself, then that sequence will just diverge because we have negative 3, positive 9, negative 27, positive 81. So it's going back and forth, plus minus, but we are taming it with an n factorial in the denominator. All right, so we can actually demonstrate this if we plug in a big number. Let's say n equals 10. Okay, minus 3 to the 10th power, that's very big, but 10 factorial, we saw 10 factorial, it's also very big. So what do we get, Maple? That much, and let's see. Can you, oh, there you go. It wanted to approximate that. First, yeah, you get a small number, 1.627 times 10 to the minus 2. Positive, of course. Let's put in an odd in picture. So let's see what happens when it's negative. So we get 15, let's say. What are we going to get? And one more time. Ooh, see, it is a lot smaller. That's 10 to the minus 2. This is 10 to the minus 5. but it is negative. Okay, so of course the terms will go to zero. They're going to get smaller and smaller, sometimes positive, sometimes negative. All right, so let's go back to our textbook and let's walk through the proof of the ratio test. It is going to sound a little bit like the limit comparison test. In fact, the idea of the proof starts out that way using epsilons. Remember the definition of convergence of a sequence, but we will also use the ordinary comparison test in order to complete the proof. Again, much like the limit comparison test where we appealed to the ordinary comparison test to complete the proof. All right, so we are given a non-zero sequence. We're going to take the quotient an plus 1 over an, its absolute value that turns it into a positive number or zero. Oh, you know what? Correction. The numerator is never zero. However, the limit could be zero, as we just saw in our first example, even though each term itself are not zero, are never zero. Okay, but we will look at the three possibilities for this limit L. It could be smaller than 1, bigger than 1, or equal to 1. So let's look at the first possibility when L is smaller than 1. So if you look at the sequence, not the series, not the partial sums, just the sequence where you get an plus 1 over an absolute value, it will converge to a limit L which is below 1. Okay, so here's 1, here's L, and we are going to get closer and closer to L. And notice that the terms are below 1. Okay, so that's an important part, but we want something a little bit stronger than that, not just below 1. Okay, so our goal is to show that the series is absolutely convergent. In other words, if you take the series with absolute values around the terms, you get a convergent series. Okay, so what we're going to do is we're going to use the ordinary comparison test on a convergent geometric series, okay, r to the n. How are we going to find this r? Okay, so first let's review the definition of the limit of a sequence, but it has to be applied not to a sub n, but to the quotient an plus 1 over an with absolute values. For any positive number epsilon, we can find an integer capital N so that if the subscript little n is bigger than capital N, then the absolute value of the ratio an plus 1 over n minus L, the limit, will be smaller than epsilon. Remember, it is this ratio, absolute value, that has limit L, not an itself. Okay, so because L is smaller than 1, we will cleverly choose the value of epsilon that will make our proof work. Okay, since L is smaller than 1, 1 minus L is positive, so half of 1 minus L is also positive. I'm going to go back to the diagram and show you what that means. Okay, here is y equals L, here is y equals 1. Okay, so 1 minus L is this gap between L and 1. That is 1 minus L. 1 minus L over 2 is half of that gap. So it is this amount, right? So that will be our epsilon. We are going to construct an epsilon strip around y equals L. And the important part is it's going to be entirely below y equals 1, right? So eventually, all of the terms below that epsilon's, beyond a certain point rather, will be within that epsilon strip. Okay, let's go back to the proof. All right, so with this value of epsilon, which appears over there, we can conclude that when n is bigger than capital N, this absolute value minus L is smaller than the epsilon 1 minus L over 2. Let us rewrite that compound inequality, that inequality with absolute values into a compound inequality. Okay, so remove the absolute values. This stays as the upper bound, but its negative becomes the lower bound. Now add L to all the parts of this inequality and simplify. Okay, so you have L minus this, 2L plus L is 3L minus 1. 2L minus L is L plus 1. So the ratio an plus 1 over an in absolute value, is between those two numbers. Okay, so what we're going to do is R will be L plus 1 over 2. Okay, so we're going to use this R for our for our geometric series. Okay, since L is positive, L plus 1 over 2 is at least 1/2. So R is also positive. But just as importantly, since L is smaller than 1, the limit is smaller than 1, when we take L plus 1 over 2, L is smaller than 1, so L plus 1 is smaller than 1 plus 1. L plus 1 over 2 is smaller than 1 plus 1 over 2, but that's 2 over 2, which is 1. Okay, so the R that we got, which we will use in a geometric series, is between 1/2 and 1. And so, two things. The epsilon strip that we get here is entirely below y equals 1, as I promised earlier. But also, the geometric series that we'll get using R to the n is going to be convergent. Okay, so let's summarize. This is what the diagram is going to look like with our choice of epsilon. Okay, so I'm exaggerating it a little bit. It probably could be a little bit wider because, as I said, this is L, this is 1, so the gap, half of the gap in between can go up to here. But I wanted to make it even worse. Okay, so beyond a certain point, we are going to be within this epsilon strip. Okay, so all the terms in an plus 1 over an absolute value are going to be within this epsilon strip and below y equals r. All right, so moving on. So when n is bigger than this capital N, which exists by the definition, an plus 1 over an absolute value is smaller than r, which is L plus 1 over 2. Okay, so the first integer bigger than capital N is n plus 1. Okay, so plug in capital N plus 1 for little n, and we get n plus 2, big N plus 2 in the numerator, and n plus 1 subscript in the denominator, which we can rewrite as an plus 2 absolute value is smaller than r times an plus 1 absolute value. Okay, now do it again for the next integer, which is n plus 2. Okay, so this will be a n plus 2 plus 1 and a n plus 2, which is what we see over there. Those are capital N stuff. All right, so we now get a n plus 3 is smaller than r times a n plus 2, all in absolute values. But we know something about a n plus 2. It is smaller than r times a n plus 1, so a n plus 3 is also smaller than r times another r times a n plus 1, which is also r squared a n plus 1. Okay, so repeat this argument. When you plug in a n plus 4, you're going to get a n plus 4 less than r cubed times a n plus 1. Okay, so in general, a n plus j is going to be smaller than r to the j minus 1 times a n plus 1. Okay, 3 becomes 2, so j becomes j minus 1. Okay, and the n plus 1 stays as an n plus 1. Okay, so we're going to bring the geometric series in, and we're going to construct a new sequence based on the old one, where up to a sub n plus 1, capital N plus 1, we're simply going to use the same terms of the original series, but we are going to use this term, because an plus j is smaller than r to the j minus 1, an plus 1, for all the terms beyond n plus, from n plus 1 and beyond, rather. Okay, so this will start with j bigger than 1, so this will start with n plus 2. Okay, this will stop at n plus 1. This will continue on with n plus 2. Okay, so by construction, I do believe that should have an absolute value. Little typo there. By construction, the absolute value of each term is at most the absolute value of these terms. So yeah, I do need an absolute value up there. Little correction. So glad we're going over this. Okay, but now, by the ordinary comparison test, if this bigger, the series built from these bigger terms converges, then the series built out of the smaller terms also converge, which would be summation of absolute value of a sub n. Okay, but then what we are looking at is essentially a geometric series. Okay, so we are looking at the partial sums Tn, absolute value b1 to absolute value of bn. And let's say that little n is big N plus j. Okay, switching notations a little bit. So we will add up to bn plus 1, continue with bn plus 2, bn plus 3, and so on. But we said, okay, these first terms are the same. They're just a1, again with absolute value though. But this term, we said, oh, that's smaller than r times the last term, an plus 1 absolute value. This one is smaller than r squared, an plus 1. This is smaller than r to the j minus 1 times an plus 1, all absolute values. But check it out, all of these terms now contain an plus 1 as a common factor. When we remove it, there's a 1 hiding there, so there's a 1 there, not 0. There's a 1 right there, but you don't see it. And the next term has r, the next has r squared, and so on, all the way up to r to j minus 1. And this is the partial sum of a geometric series, and we said that this series is convergent, so therefore that partial sum will converge to some real number. And so, once again, by the OCT, our smaller series summation absolute value of an also converges. All right, so now what happens if our limit is bigger than 1? So we're going to go through the same argument, except there's a difference that L is bigger than 1. So this time, L is above 1, so L minus 1 is positive. Our epsilon will be L minus 1 over 2. Last time it was 1 minus L over 2. But this time L is bigger than 1, so we have to do L minus 1 over 2. Okay, so we have our inequality involving epsilon. And again, we construct the compound inequality, and we get, this time, L plus 1 over 2 smaller than absolute value of an plus 1 over an. Okay? But L is bigger than 1. We can still see it over here. So this time, if you want L plus 1 over 2, which is this smaller number, it's going to be bigger than 1 plus 1 over 2, or 1. Okay? So therefore, we can write this as absolute value of an plus 1 over an. Let me get out of the way here. Too much. Right there. And let me scoot up here. Okay, so an plus 1 over an is going to be bigger than L plus 1 over 2, which is bigger than 1. So L plus 1 over 2 is going to be here, bigger than 1. This is going to be our epsilon strip, and eventually our terms are within that epsilon strip. Notice how those terms are way above 1. Okay, so therefore, what we're going to get is that the series, the sequence must be, the series must be divergent, because we can now see that an plus 2 is bigger than an plus 1, kind of like before. And continuing, we will get that an plus 3 is bigger than an plus 2. So we get an increasing sequence, all right? So starting with an plus 1, an plus 2 is going to be bigger in absolute value. An plus 3 is even going to be bigger. Can it be possible for the terms to go to 0? Of course not. They're getting bigger and bigger in absolute value. So the terms cannot converge to 0. By the test for divergence, our series with our series with just an must be divergent, not absolute value. This argument tells us that the terms cannot be going to 0 without the absolute values, and so our series without absolute values must be divergent. So there is a part 3 which says if the limit is 1, you cannot form any conclusion. We're just going to show that it is possible. It's very easy to get a limit of 1. Just use any p series. So we have n to the p, replace n with n plus 1. We get n plus 1 to the p, not p plus 1. Okay? N is the base, not the exponent. So we have n plus 1 to the p over 1 over n to the p. Again, flip. We have n to the p over n plus 1 to the p, which we can write as quantity n over n plus 1 to the p. We know that n over n plus 1 goes to 1. P you can think of as a constant. Again, there's no n there. All right, so that ratio goes to 1 to the p, which is equal to 1. Okay, we know that when p is 1, we get the harmonic series which diverges. If p is bigger than 1, we get a convergent series. So when this happens, you cannot make a conclusion. You can get a divergent series or you can get a convergent series. So therefore, the ratio test is inconclusive. Okay, let's look at one more example, something a little bit more complicated this time, similar to something in your homework, and back to our workroom. Okay, we injected steroids into our first example. Again, it's alternating, but we have 5n plus 1 to the power 2n in our numerator. We had only minus 3 to the n before, so now we see n also in the base. And this time, instead of n factorial, we have quantity 2n factorial. So, let's start out with that, okay? 2n is an even number, okay? So we already saw that we can get 6 factorial, which is 6 times 5 times 4 times 3 times 2 times 1. We know it's 720, but the point here is to look for patterns, okay? So if n is 3, you will get 6. n equals 3 means 2n equals 6. And we get 6 factorial to be this. Okay? So what would n plus 1 be? Okay, remember we're going to look at an plus 1. n is 3, so n plus 1 is 4. So that means that 2 times n plus 1 equals 8. Not 7, but 8. Okay. So 8 factorial is going to be 8 times 7 times 6 times 5 times 4. So let's put 6 here. And then the rest is 5, 4, 3, 2, 1. 8, 7, 6, 5, 4, 3, 2, 1. Counting backwards. Okay? So what is the difference between 8 factorial and 6 factorial? 6 factorial is over here. So we have an extra 8 times 7. We get 8 times 7, and then the rest of that product is 6 factorial. Okay, so that's very important. The difference between 8 factorial and 6 factorial involves two numbers, 8 and 7. Before it was just one number. The difference between 5 factorial and 6 factorial was only 6. This time we have 8 and 7. All right, so with that, hopefully we can understand an plus 1 a little better. So we're going to copy an again, encircle all the n's that you see in an and change them to n plus 1. 1, 2, 3, 4. We see n 4 times. Change all of them to n plus 1, wrapped in parentheses if need be. Okay, so we need it here for 5n plus 1, so that becomes n plus 1. I'm going to use square brackets because it's a little bit easier to see it with square brackets. So 2n, wrap it in brackets, n plus 1. 2n within the parentheses, wrap in brackets, n plus 1. Okay, so we need to simplify this. All right, so we are going to distribute 5n plus 5 is 5n plus 1 quantity is 5n plus 5 plus 1. 2n plus 1 distributes to 2n plus 2. Okay, be very careful. And we have another 2n plus 1 here, which distributes to 2n plus 2. Okay, so far so good. So now we are going to work on this a little bit more. So that is simply 5n plus 6 to the 2n plus 2 and 2n plus 2 factorial. So remember what happened here. There are 2 extra factors before we got to 6 factorial. So in the same way, remember you count backwards. So 2n plus 2 factorial means you start with 2n plus 2, you multiply to the integer below that, right below that, subtract 1, 2 minus 1 is 1. Keep going, we're not yet finished. You're going to get 2n plus 1 minus 1, so it's simply 2n. And then, after that, is 2n minus 1. And so on until we get to 2 and 1. Okay? 8, 7, 6, 5, 4, 3, 2, 1. All the integers from 2n plus 2 all the way down to 1. Okay. What else can we do? Well, that power, 2n plus 2, can be rewritten just like we had minus 3 to the n plus 1. We can distribute, sort of, where we will have 2n as the first exponent and just 2 in the second exponent. Okay, so there's a product in between there. Okay, let's just make sure you see that this becomes the product, 5n plus 6 to the 2n, 5n plus 6 to the 2. Okay, not 1, but 2. Be very careful with that and with this. Okay? But now, what is 2n times 2n minus 1 and so on? We saw that there's a 6 factorial hiding in here. So this portion of our program is brought to you by 2n quantity factorial. Okay, so let's exaggerate. Okay, so let's make sure that we see that we have the 2 extra factors, like the 8 and the 7, times 2n factorial. Okay, so I do believe I am happy with this simplification. So now, let us construct an plus 1 over an absolute value to take the limit. All right, so we are now ready to take the limit of the ratio, an absolute value, of course. So this is our an plus 1. This is our an. Okay, so I just copied it from the original series, of course. Remember what I said. To save time, you don't have to take this and divide by this. You can take this and multiply by the reciprocal of this. And another thing, one more thing which I didn't mention earlier, we're taking the absolute value for heaven's sake. Do we really need that minus 1 to the n plus 1? Of course not. It's simply going to become positive 1. So as far as an plus 1 is concerned, all we need is that, where everything is positive, actually. And as far as an is concerned, we only need this part, but again, not divide, we're going to multiply by the reciprocal. Okay, so take the reciprocal, the 2n factorial goes in the numerator, and the 5n plus 1 to the 2n goes in the denominator. Okay, so let's make sure we see that that's a product. Let's put a times there in between. Okay, so that looks pretty bad. Yeah, I said the problem, we injected some steroids into our first example. So we're going to simplify. What cancels right away? Okay, 2n factorial cancels with that 2n factorial. Okay, excellent, right? When we delete, make sure that the factorial goes away. So, close call. Okay, so the whole thing 2n factorial cancels with the 2n factorial over there. We are left with just 2n plus 2 and 2n plus 1. Okay, so you might say, all right, well, where is this going? What we're going to do next is we're going to put the apples together with the apples and the oranges together with the oranges. Okay, what do I mean by that? Well, there's 5n plus 6 to the 2n here, 5n plus 1 to the 2n there. Okay, so both of them share a 2n in the exponent. So what I'm going to do is I am going to scoot this over to be under the 5n plus 6 to the 2n, and I'm going to move these three other factors to the other quotient. Okay, so 5n plus 6 squared stays in the numerator, 2n plus 2 times 2n plus 1 stays in the denominator. Okay, I'm just rearranging the furniture. The numerator terms, factors, stay in the numerator. Right there, right there. The denominator factors stay in the denominator. Right here, moves to the left. Okay? All right. And now, I'm going to do one more step. Both of these are to the power 2n. So what I'm going to do is, I'm going to put them together into a single fraction raised to the power 2n. Okay, so I'm going to take all of this. You can still see where it came from, but I'm going to remove the 2n there, and I'm going to remove the 2n there. Okay? 5n plus 6 to the 2n, 5n plus 6 to the 2n, 5n plus 1 to the 2n, 5n plus 1 to the 2n. Everything is there accounted for. A to the, what's the property? A to the x over b to the x is the same as a over b to the power x. Okay? All right. So now, by the way, these are, of course, all equal to each other. Equals and equals and equals. Okay. What we're going to do is, we're going to show that both of these factors have a limit at infinity, and so we are allowed to multiply them together. So what I'm going to do is, I'm going to write a product of two limits. Whoops. This has to go over here. And I'm going to keep the factor on the left, and I'm going to keep the factor on the right. There we go. Oh, absolute values. Do we really need the absolute? That's positive, positive, everything's positive. So yeah, we need that limit multiplied by this limit. Okay, so now I'm going to remind you of something before we attack these limits. What are we looking at here? N is going to infinity, getting bigger and bigger. 5n plus 6 getting bigger and bigger. 5n plus 1 getting bigger and bigger. Infinity over infinity. Oh, but wait, we know L'Hopital's rule. So infinity over infinity, the derivative is 5, the derivative is 5. Ooh, the limit is just 1. We're also back to basic calculus. If you simply divide numerator and the denominator by n, we're going to get 5 over 5, which is 1. The other terms go to 0. So the base has limit 1. The power, though, is 2n, and n is also going to infinity. It's the same n, so 2n is going to infinity. So we're getting 1 to the infinity. Okay, and this is where I remind you of something. Okay, remember this? This was the video. This is from the video about L'Hopital's rule and indeterminate forms. L'Hopital's rule only applies when you have these two forms, 0 over 0 or infinity over infinity. That's why we were able to use it on 5n plus 1 over 5n plus 5. That was perfectly legal. It does not apply to indeterminate products or differences or powers. Okay? Our problem is very similar to this one. Okay? We have 5x plus 1 over 5x plus 5n plus 6, something like that, to the power 2n. Okay? It's almost the same as this one, except for different numbers. Okay? So, you remember the strategy. If you have something like this, set it equal to y, then take the logarithm of both sides of that equation. The power drops because of the properties of logarithm, and now you have an indeterminate product, but you can turn it into a fraction by flipping one of the factors. And of course, the power is the easier factor to flip down. Okay? So if you have forgotten that, check it out, right? It is video lecture 11. Okay, so to compute the first limit, we set y will be this whole thing, including the exponent. So ln of y is the ln of this thing. And by the proper properties of logarithms, that is 2n times ln, ln of what is inside the brackets. Okay. So again, this has limit 1. ln of 1 is 0, but n is going to infinity. This is an infinity times 0 form. And in order to have a form that allows us to use L'Hopital's rule, we have to convert it to a quotient. So we have ln in the numerator, n flips down to the denominator as 1 over n. Okay? Or if you like, n to the minus 1. Okay, so this is now 0 over 0. So we can now apply L'Hopital's rule. By LH, the last quotient has limit. Okay. Oh, by the way, remember the trick that we did when we saw this, we can distribute the numerator, again, using the properties of the logarithm, this time the quotient property. So we have ln of 5n plus 6 minus ln of 5n plus 1. Are you going to fit 5n plus 1? Oh yeah, just about. Okay, so that's still 0, even though it looks like infinity minus infinity. It came from this. All we did was algebra. So this limit is still 0, not infinity minus infinity. Okay, so we can now find the limit. We can keep the 2 outside. We'll take the derivative of the numerator over the derivative of the denominator, because that's how L'Hopital's rule works. So we have 1 over 5n plus 6, chain rule times 5, minus 1 over 5n plus 1 over 5. Oh, so I can recycle this and turn the 6 into a 1. Okay, so derivative of ln 5n plus 1 is 1 over 5n plus 1 times 5 by the chain rule. Derivative of the denominator, n to the minus 1, becomes minus 1, n to the minus 2. Haha, there we go. Okay, so now algebra, we simplify. Oh, we can take the 5 out, and we're going to get 10 with the 2. And what are we going to get? What are we going to get? So the 5 there becomes 1, and a 1 over here, and then we'll combine the fractions. Okay, so let's do that in the same step. 5n plus 1 cross over here, minus quantity, careful, 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 quantity 5n plus 6 over here. And we are going to have a common denominator. So here's what we're going to do. We'll put parentheses here and another pair there. And we're going to put 5n plus 1 here. And we'll put the minus quantity 5n plus 6 to the right of 5n plus 1. Okay? Review. Factor out the 5 times 2 makes 10. And we get 5n plus 1 minus quantity 5n plus 6. Common denominator 5n plus 6, 5n plus 1. All over minus n to the minus 2. Okay, so next step. Simplify. Never underestimate the power of doing the arithmetic and the algebra. Okay, 5n plus 1 minus 5n, careful, minus 6. Okay, so the 5n's cancel, and we get 1 minus 6, or negative 5. So I'm going to do this. 5n's cancel, 1 minus 6 is negative 5. Okay, but keep going. We can simplify that fraction. We get the 10. There are 2 minuses there, so that becomes plus. And we get 1 over n to the minus 2, which goes up into the numerator as n to the positive 2. So I'm going to do this. Let's put brackets. The minuses go away. And we have n squared in the numerator, because 1 over n to the minus 2 is the same as n to the positive 2. All right, so now what do we get? N squared here, 25n squared there. We are taking a limit, so that limit is just 1 over 25. So we can now use the arrow symbol. That has limit, which is 10 over 25, which reduces to 2 over 5. All right, 2 over 5. Or 0.4. Okay, so we are not yet done, almost done, because we took the ln of both sides. Remember that part? We took the ln of both sides. The limit is 2/5. So y itself, which is this whole thing, will be e to the 2/5. Okay? Thus, ln of y goes to right arrow 2/5, comma, and so y itself goes to e to the power 2/5. How much is that? Oh, Maple, you're approximately 1.49. Okay, so let's verify. Let's take this original expression and let's make sure that if we plug in a big number like n equals 10, we're going to get something close to 1.49. Maple does not like brackets. I use it only for typesetting because it's nicer to look at. So change that to round parentheses, and what have we got? 6.49. Ooh, I don't like that. Oh no! Yes, there was a mistake, but I found it. So what happened here? It's correct up here. We canceled the minuses, flipped the n squared in the numerator. We left out the 5. No, correction. I left out the 5. My mistake. So there's an extra 5 there, but there's a 25 there. So that limit is just 5. 10 over 5, which is equal to 2. So ln of y converges to 2. And so y itself converges to e to the 2. And what is e to the 2? E to the 2 is about 7.38. Oh my, that is not close, too close to this number. But we only plugged in n equals 10. What happens if we plug in n equals 100? We're gonna get 7.287. A lot closer, don't you think? All right, so that is the correct limit for the first factor. Okay, it is just e to the 2. So let's go back to where we were, which was this. Okay, so let's copy it down here. We wanted this limit. Okay, so we know that this first limit is e squared. All right, but what about this second limit? Right? Oh, this one's easier. We have 5n plus 6 squared, so we get 25n squared. 2n plus 2, 2n plus 1, so there's 4n squared in the denominator. Okay, so we did the hard part. The first factor is e squared. The second one is 25 over 4. Where's my fraction? There you are. 25 over 4. Okay, I don't have a good feeling over this. Are you bigger than 1? It is definitely bigger than 1. All right. So thus, since L equals 25e squared over 4 is bigger than 1, our series, our original series, is divergent. Like part B of the ratio test. All right, so that is it for the ratio test. In the next video, we are going to look at a similar test called the root test, and that will be the last video for part 2 of our textbook. After that, we will be going on to our series. All right, but until then, I hope you enjoy the rest of your day. Bye.